Swayam Prabha. Digital India. Educated India.
What is this? Iridium. Iridium is below cobalt. Cobalt, rhodium, iridium. Do the electron count for the whole molecule, I am asking. Iridium 9, triphenyl phosphine will be triphenyl phosphine is a phosphine ligand. Ammonia, phosphine, carbon monoxide, 2 electrons. Okay. Iridium is 9. Triphenyl phosphine 2, carbon monoxide and chlorine total 16. So this is a square planar 16 electron compound. And the calculation we did now is by neutral method. Let's do by charge method now. PPH3 you do not put charge. CO also do not put charge. Chlorine we can say Cl minus. If we say Cl minus, iridium will be plus. Then calculation will be now iridium plus. That will be how many electron?
8 electrons.
Then Cl2. So total becomes 16. So now I insist the charge. Okay. This compound is iridium plus charge. This compound has a name. Do you know what is the name? Are you aware of this name? Baskas complex? No? This is called Baskas complex. Iridium 2 times triphenyl phosphine in transposition, CO and Cl 16 electron compound. So this is 16 electron compound. This reacts with hydrogen. Consider that one molecule of hydrogen is coming like this and pushing the CO and Cl behind. And this place is occupied by those 2 hydrogen atoms. So this dot line indicates here bond is broken but not completely broken. And this indicates that bond is formed but not completely formed. And this is not dotted line, this is hash line which is behind, right? So this line and this line meaning is different. That hash kind of thing is behind the plane and dot kind of thing is partial bond. In this case, hydrogen molecule approach towards the metal and start forming bond. And slowly this bond will form completely and this bond will break. Okay. H is considered H minus if we put charge. Cl is considered Cl minus if we put charge. So this iridium become no plus 3. It was plus 1 there. Now one negative charge here, one negative charge here, one negative charge here. So iridium 1 plus become iridium 3 plus, and 2 hydrogen atoms become the new ligand. In this process, what has happened is called oxidative addition. Now you understand what is oxidative addition, and with example, the coordination number here is how many? 4, and here 6. Oxidation number here is, and here plus 3. So oxidation number increases by 2, 1 become 3. Coordination number increases by 2, 4 becomes 6, and 2 ligands are there now. So this is called oxidative addition reaction. The reverse should be called, the reverse of oxidation is reduction, reverse of addition is elimination. So whenever a 6 coordinated compound, 2 ligands comes out, form a bond and goes away, and a coordination number now decrease by 2, oxidation number also decrease by 2, then that is called a reductive elimination reaction. This is called a oxidative addition reaction. Let us say instead of hydrogen, this also react with oxygen molecule. If it reacts with oxygen molecule, then what will happen? One oxygen atom will be here, one oxygen atom will be here, and between the oxygen atom there will be one bond, because oxygen, there is a double bond. What is broken here is one of the bonds, not both. So if it is hydrogen, bond is completely broken, they have become individual. If it is an oxygen molecule, they are still attached with each other, because there are 2 bonds between them. So when viscous complex react with hydrogen, it forms a compound like this. If it react with oxygen, this is when it react with oxygen molecule. So the position of these 2 hydrogen is called cis to each other. This and this are trans, right? This and this are trans. These 2 are cis. So during oxidative addition, the incoming group, they remain cis to each other. Okay. Provided the one which is reacting is non-polar. H2 is a non-polar compound. If we react with methyl iodide, let us say, methyl iodide, then first this one attack to methyl, iodide goes out, and after that, that iodide again come back and connect. So in that case, iodide can come to the trans position. But if it is a non-polar compound, the bond formation and bond breaking happen simultaneously, concerted mechanism, hence the 2 groups become cis to each other. So now you learn little bit about oxidative addition, and the reverse is called reductive elimination. Then I tell you about another reaction. So this is called oxidative addition, reverse is reductive elimination. Now MnCO5CH3, you are now familiar with this compound. If you put more carbon monoxide, put under the pressure of carbon monoxide at lower temperature, then this compound changes to MnCO5CH3 become MnCO5COCH3. And what is that COCH3? Acetyl group. CH3CO is called acetyl group. CH3COCl, acetyl chloride, CH3COOH, acetic acid. So, one extra carbon monoxide become the part of the molecule now. Like CH3 is a 1 electron donor. CH3CO is also 1 electron donor. CH3CO dot Cl dot or CH3CO dot H dot, think like that. So, number of electron count is not changed. 18 electron remain 18 electron. Formula changed. The methyl changed to acetyl now. MnCO5CH3 become MnCO5COCH3. Okay. Alright. So, now what happened? This CO here, does it enter between manganese and methyl bonds? Before that it was let us say that was the compound. Okay. In MnCO5CH3, the position of CH3 could be anywhere. Instead of here, I can put the methyl here also. Here, anywhere you want to put, no problem, right? Because in a octahedral compound, 5 positions are carbon monoxide, 1 is a methyl, right? So, if let us say this is the MnCO5CH3, all these things which nothing is put there, consider they are CO, and this is the methyl. The way I showed here is like that, right? But if I do like this, no problem. If I do like this also, no problem. So, the position of methyl could be anywhere. The way you draw, that's up to you. If you want to draw here, no problem. Draw here, no problem, right? So, MnCO5CH3 I draw like this, MnCO5COCH3 I draw like this. Likewise, COCH3 I can draw anywhere, right? It could be drawn anywhere, no problem. So, I decided to put it there. Now, I will give you a surprise. Red color to distinguish. And generally, chemically, how to distinguish? By taking 13C. You know about leveling? 13C, leveling experiment. If you put a carbon 13, that is called leveling. Let us say we take carbon monoxide, which is 13 carbon, pure 13 carbons here, put it there, excess up and react this thing. Now, we will be able to distinguish here, where is that red one? What do you expect the red one to be? Let me put the positions 1, 2, 3, 4, 5 and 6 position. So, the position of the red color carbon monoxide will be 1. How many think it will be 1? Okay. And other people I will not ask, because I already know what you are. At least few people are brave enough to attempt. If you do not attempt, there is no negative marking now. Okay. Alright. So, the truth is something different. It is here. Okay. Surprising, right? That is the truth. It is not there. And when you say there means either here or here or here or here, all are equal. There is no difference. With respect to this is cis position. With respect to this is transposition. So all these 4 carbon monoxide position wise equivalent. If we say this one, then position wise different. So anywhere you put, that will be cis. Acetyl group and red color carbon monoxide, or the labeled carbon monoxide, or 13C carbon monoxide, that one is cis. This is a cis. That means when we look at this reaction and the formula, it obviously appears like probably carbon monoxide enter in between here. But experimental fact says that it's not like that. If it has not entered between manganese and methyl bond, and if it is elsewhere, then where from this carbon monoxide come now? It has to be only from here, because you did not add the white carbon monoxide. So one of the remaining thing has gone there. Okay. What happens if I draw the formula slightly differently? Let's say same thing, right? Is it different? No, it's the same thing. So here it appears like the carbon monoxide from here got removed, entered there. A vacant space is created here, and that vacant space is occupied by red carbon monoxide. But I make an illusion now, draw the formula like that. Then you will think probably the methyl from here has gone there, creating a vacant space where the red carbon monoxide comes. 2 ways of thinking. Just because I draw in this way or that way, you are getting influenced. The right hand side diagram looks like one of the carbon monoxide which is from here has been detached and got inserted. It looks like that. And here the other way. It appears like methyl has gone there and this has come. But these two, are they any different? They are not different. Just because I draw in this way, your thought process changes. But chemically they are not different. But anyway, either methyl has migrated to carbon monoxide releasing a free space, or carbon monoxide has migrated to methyl releasing a free space, or both has happened. Right? These are the possibilities. And to that free space, carbon monoxide has come. So it's guaranteed that one of the carbon monoxide is detached, right, by migration or receiving methyl. In that case, methyl is detached. Either methyl is detached, gone to carbon monoxide, or carbon monoxide is detached, gone to methyl, or both. Certainly not that the red one has entered here, because experimental facts say that the acetyl CO is not the red one. Okay. So this is called insertion reaction. If you do not know the red color or 13CO, then initially you will think carbon monoxide enter between manganese and methyl. So that was the initial thought when people got this reaction. They called it the insertion reaction. Even today it is called insertion reaction, but actually instead of insertion reaction, we should say migratory insertion reaction, because something is migrating. Either methyl is migrating or carbon monoxide is migrating. So actual term more appropriate is migratory insertion, but sometimes it is also called insertion. Mostly it is called insertion, and the term is so much used that no need to say migratory, it is understood. When this reaction was made, that time it was not known. People thought it is insertion. After several more years only people got the mechanism and they realized this migration. Hence the term was changed to migratory insertion, but the name could not be completely changed. Okay. Like do whatever sometime people call Chennai as Madras. Both are correct. But technically Chennai is correct. So in that way, this is called, so what you studied is oxidative addition reaction, reductive elimination. Then insertion reaction, more correct is migratory insertion. The reverse of it would be called de-insertion reaction. Insertion, de-insertion. Okay. And what happens is, if you go to the detail in the book, or I don't have time to do the mechanism and prove it, methyl migrates, not carbon monoxide. Manganese methyl bond breaks, it goes to carbon monoxide. Not that carbon monoxide breaks and enter inside. That is the actual finding by mechanistic study people have got it. So remember this thing as a methyl migration, not carbon monoxide migration. Okay. And I will not go to the further detail of that. So oxidative addition, reductive elimination, migratory insertion or insertion reaction. If carbon-carbon double bond is connected to metal and the cis position there is a hydrogen atom, sometime this migration can happen, making it CH2, carbon-carbon double bond and one hydrogen. This is also migration, right? And the reverse is called elimination. It's called beta elimination because this is alpha position, this is beta position. So sometime in this way it goes, this is called beta elimination, and this way it will be called migration. Okay. Do you know what is Wilkinson's catalyst? What is the formula? What is the metal? Rhodium. What are the ligands around it? Triphenyl phosphine. So what is the formula? Wilkinson catalyst you should be able to know. That formula is there. You read it somewhere, right? What it is? Tell me. Try to say something. Rhodium. Rhodium. Then how many? Then this is called Wilkinson catalyst. This is used for what reaction? Hydrogenation is correct. Hydrogenation of alkane. So Wilkinson catalyst is used for hydrogenation of olefin, right? Olefin hydrogenation. For example, carbon-carbon double bond, CH2 double bond CH2 become CH3 by adding two hydrogen. This is olefin. A molecule of hydrogen comes, add there. Carbon-carbon double bond, across that hydrogen molecule is added. This is called hydrogenation of olefin or alkene hydrogenation or conversion of alkene to alkane. That can be done using Wilkinson catalyst. Typically, before Wilkinson catalyst, people used to take Raney nickel, hydrogen, high temperature, high pressure to do this reaction. Conversion of alkene to alkane by hydrogenation reaction is thermodynamically feasible reaction. If you say reaction coordinate, do you understand this kind of diagram? Energy profile. This is the barrier. This is the energy of the reactant. This for the product. If this one is below, that's a feasible thing, right? If it is like this, then that's not a good thing, right? This is good. But if this barrier is too huge, even though thermodynamically it's okay, but the barrier become very huge, it's not able to go to the other side, right? And if barrier is small, it can be done easily. If it become too huge, even though this is stable, it cannot be done. So this hydrogenation of olefin is such a case. The product is very stable compared to the reactant, but the pathway is such that the barrier is such that it's so high, so it cannot move. Hence, the Rennie nickel, very high temperature, very high pressure, those things helps to make it. And because of high temperature, high pressure, it's a reaction which is dangerous. So Wilkinson catalyst, it could do it at room temperature without high pressure, without high temperature. Hence, it become famous. And how it happens? By using this thing as a catalyst, something happens in between. So whenever catalysis happen, the catalyst participate in the process, and at the end of the reaction, it comes back to the same state. So the Wilkinson catalyst, rhodium PPS3(3)Cl, that's the starting point. Olefin and hydrogen react with each other, and catalyst plays a role. At the end, product is formed, catalyst is again come back to the next round. So that we will see now. What do I write now? Okay. What are the molecules that we put there? Carbon-carbon double bond olefin and hydrogen. Of course, solvent is there. It's a homogeneous condition. In some solvent, catalyst is taken, olefin is taken, hydrogen is taken, and it reacts. So that means something reacts with something at the beginning. What would happen? Only olefin and hydrogen, they do not react with each other because the energy barrier is too huge, right? Only hydrogen, can it react here? Just now I told you. Oxidative addition. Okay? It can undergo oxidative addition. By the way, this is how many electron compound? Cobalt, rhodium, iridium, everything in the same column. I removed one. So total is 16 electron, 18 electron, 17 electron. Earlier Baskas complex was how many electron? 16. If I change from iridium to rhodium, any change? No change. If I remove one carbon monoxide, put a triphenyl phosphine, any change? In electron count, no change. So this compound is also 16 electron compound. 16 electron compound, this can undergo oxidative addition with hydrogen, not olefin, hydrogen. Hydrogen comes and it reacts here, making a hydrogen metal bond. Hydrogen bond breaks, hydrogen metal bond is formed. Okay. Oxidative addition happens. If the olefin and hydrogen both has to react now. Triphenyl phosphine, they are bulky groups. In organometallic chemistry, whenever you show a reaction, they are all reversible reaction. We put it both side arrow. Okay, they are reversible. This way, that way it can keep on going. So when it adds to hydrogen, like that, this can be dissociated. One of the triphenyl phosphine, it can dissociate. One triphenyl phosphine is dissociated. Okay, this is a 16 electron compound. This one is, it has to be 18 electron compound. And when triphenyl phosphine is dissociated, that become, it has to be 16. This place is occupied by olefin. Olefin is a 2 electron donor. Then again it becomes 18 electron compound. Now hydrogen and olefin, there is a migration. Sometime back I told you migration. If this hydrogen is migrated to here, then it will be like RCH-CH2 become RCH2-CH2. This carbon is now connected to metal. Hydrogen goes there, become RCH2, and that is also CH2. So that carbon connects to metal. And this side will become free. If this hydrogen from here migrates, that becomes free. That free site can be occupied by either solvent molecule or triphenyl phosphine. Let's say a triphenyl phosphine comes there. Reductive elimination means if two groups together comes out from the metal. Oxidative addition means two groups are added. Reductive elimination means two groups come out. When they come out, they form a bond between them. So this RCH2-CH2 and H, together they come out forming a bond, releasing the alkane. Okay. So what happened? Initially, Wilkinson catalyst undergo oxidative addition. Then one ligand is dissociated. That place is occupied by olefin. So you can either call it a substitution reaction, or we can call dissociation followed by association. If triphenyl phosphine is lost, that is a dissociation. If olefin comes, that is a association. But if it happens at a time, it's a substitution. So unless the triphenyl phosphine goes out, there is no place for olefin. And in between, the olefin become alkyl and the alkyl become alkane by reductive elimination. So the concept of oxidative addition, concept of reductive elimination, concept of migration, whatever I told you previously, all those concepts are here now. And at the end, the catalyst comes out for the second cycle. In the organometallic catalysis, if you check some other book, there may be slightly different thing. Okay, the catalysis mechanism cannot be proved very certainly. This is a tentative mechanism. proving the mechanism of a catalysis reaction is very, very difficult thing. Whoever has said all this thing, how did they do it? They must have done some experiment, some proof that these are the things which is forming. And some people come and say, no, it's not like this. This triphenyl phosphate is not here, it is there. So all these arguments are there. So from one book to another book, you may find slight difference. This one of the mechanism is first step, addition of hydrogen by oxidative addition. There is one more mechanism which is also equally valid. In the first step itself, one triphenyl phosphine is lost. Then hydrogen is added. In this mechanism, first step addition of hydrogen, then loss of triphenyl. Just reverse of it. Means before hydrogen is added, one triphenyl phosphine is lost. And that amount, there is an equilibrium between this one and the one having triphenyl phosphine lost. This is in major amount and the other one is in minor amount. This exists in equilibrium with P for triphenyl phosphine. One triphenyl phosphine is lost. A tri-coordinated compound, not some T-shape kind of thing, and that is minor amount. This can also undergo oxidative addition with hydrogen, forming a 5-coordinate compound, and that also participate in a similar way. Even though that one is minor and this is major, this one is much more reactive. This one is less reactive. When it goes for 10-15 cycle, by that time the other one would have gone for 1000 cycle. Even though the amount present is very minor, its reactivity is very high. So both mechanisms are usually seen. In some book gives this mechanism, some books give that mechanism, some books give both mechanisms. So in this book that I showed you, both mechanisms are shown there. So you read by yourself, satisfy yourself looking at the mechanism and try to understand a little bit more. So this is called hydrogenation of olefin using Wilkinson catalyst, which utilizes the concept of oxidative addition, reductive elimination, migratory insertion, 16 electron count, 18 electron count, all those things. The 16 electron compounds are generally reactive compounds, because even though they follow 16 electron rule, they would be happy to go to 18 electron also under certain situation. So the play between 16, 18, 18, 16, etc. drives the catalysis. Okay. And when the catalysis happen, one cycle catalysis is done. Then that catalysis is utilized for the second cycle, then for the third cycle, and so on. So if you add more amount of catalyst, each molecule are working simultaneously. If you add less amount of catalyst, then less number of molecules are there. So when you need more number of catalyst, if they are slow, if one catalyst is running very fast, is running 1000 cycle in second, another is slowly running, then there you need more thing because you want to finish the job. Okay. So one cycle is called one turnover. One cycle is called one turnover. And how many cycle it goes, that is called turnover number. Suppose you have certain number of catalyst, each catalyst is running cycles by cycles. Before it stop working, at some point of time maybe it will die. It may come to some situation where it is not effective anymore, then it cannot do the catalysis anymore. So that is called how many cycle it has gone. That is called turnover number. So therefore, a catalyst which gives more turnover number, that would be liked by the industry. If some catalysts die after one cycle, some catalysts go for 1000, some go for 10,000, some go for 1 lakh. Whatever go for more number of cycle, those catalysts will be liked by the industry. That is called turnover number. There is something called turnover frequency. It's going for so many number of cycle, but what happens if each cycle is going slowly? Even though it is not dying, but it's going slowly. So let's say something is not dying and going very fast also. Then turnover number is important. Turnover frequency is also equally important, which goes faster. Okay. Per hour, how many cycle it run, or per second, how many cycle it run. That's called turnover frequency. So turnover frequency is turnover number divided by time. Suppose turnover number is 10,000. And turnover frequency, if it happens in 10 minutes or if it require 1 hour, if it require 1 day, the longer it require, the turnover frequency is smaller. So when turnover number is high, turnover frequency is also high, then industry will like that catalyst. So it's called TON and TOF. T for turnover or TO, TON for turnover number, turnover frequency. Turnover frequency is TON divided by time. If you take turnover number is a number, no unit. Time has a unit. If you put seconds, then turnover frequency second inverse. If you take hour, turnover frequency some number hour inverse. If it is day, then day inverse. So the turnover frequency, that number depends upon what is the unit of time, right? So you cannot say that I change it to some other thing and my turnover frequency looks good. No, you have to look at unit also. So turnover, turnover number, turnover frequency, these three terms you can check by yourself. And this is one example of a catalytic cycle. Okay. So in your CSR UGC net, those who are interested in appearing in organometallic chemistry, you have catalysis cycle where you have hydrogenation reaction and some other reactions like let's say this is called hydrogenation reaction. Two hydrogen atoms are added. Instead of H and H, H and CHO is added to make a aldehyde. This is called hydroformylation. H is hydro, COH is formyl. Hydroformylation reaction. The catalyst required here is Wilkinson catalyst and the other reactant is H2. In the hydroformylation reaction, HHCO. So hydrogen and carbon monoxide. This require hydrogen and carbon monoxide both. But the catalyst is different. In the first case, Wilkinson catalyst, reactant is hydrogen. Second case, reactants are hydrogen carbon monoxide and the catalyst uses CO2, CO8, dicobalt, octacarbonyl. That is the catalyst. So I give you assignment, look at the book, draw the catalytic cycle for hydroformylation reaction. Okay? Hydroformylation reaction, draw the catalytic cycle. CH3OH methanol, CO carbon monoxide. CH3COOH is acetic acid. So methanol goes to acetic acid. Again it appears like CO enter inside here, right? But that is not so. It appears like this from this reaction, but the mechanism shows something else. The end product may be so. And in this thing, there are few other things. Some catalyst is required, some co-catalyst is required, some other things are required here. Find out what are those. This is called methanol and carbon monoxide reaction or acetic acid process or Monsanto acetic acid process. Okay. Hydrogenation. hydrogenation, hydroformylation. This is called Monsanto process. Monsanto process or Monsanto acetic acid process or methanol carbonylation. Okay. Then something called Walker process. So what I have done, I showed you the catalytic cycle of hydrogenation. I explained you the steps, how the reactions are, what kind of reactivity happening. A very similar kind of things are there. Therefore, I will not go again and again the shortage of time. You do by yourself hydroformylation reaction, which is conversion of olefin to aldehyde. You do by yourself methanol to acetic acid, looking at the book or whatever source. And there is something called Walker process. Here, I will not tell what is the reaction. You find out what is the reaction, what is the catalyst, how it reacts, what product is formed. Okay. So now, calculating number of electrons should not be a problem for you. If it is a problem, you can read the book and understand. Right? If you read few times, you should be able to understand 16 electron, 18 electron calculation. You understand the concept of the oxidative addition, reductive elimination, insertion reaction. I showed you on catalytic cycle. Hence, you should be able to do by yourself now hydroformylation, Monsanto process and Walker process. Okay. So, this is the assignment for you. And if you have doubt, I will be coming once again to teach another topic in the afternoon. After the topic is discussed, if you have some doubt on this organometallic chemistry, you can ask me, or if you want to ask me later on, that will be difficult for you to find me where I am, and you are also quite busy for so many classes. Whatever is suitable for you, find out. If you want to ask me, I am available. After going from here, if you have some doubt, find out my email address from website, contact me. If you have any need, any advice required, I will be available for you. I will see you in the afternoon at 2 o'clock to teach another topic. So, that is all for now. So, you have got some flavor of what is organometallics in catalysis. That was the topic for today. Okay? Everything is fine? Alright, so I will see you in the afternoon.
SwayamPrabha, Digital India, Educated India.